Hi everyone, today we're doing notes for 7.4, estimating mu1 minus mu2 and p1 minus p2. So, independent samples. Two samples are independent if sample data drawn from one population are completely unrelated to the selection of sample data from the other population. Dependent samples. Two samples are dependent if each data value in one sample can be paired with a corresponding data value in the other sample. So, for each experiment, categorize the sampling as independent or dependent and explain your choice. So, letter A. In many medical experiments, a sample of subjects is randomly divided into two groups. One group is given a specific treatment, and the other group is given a placebo. After a certain period of time, both groups are measured for the same condition. Do the measurements from these two groups constitute independent or dependent samples? So in this case, they are independent samples. And this is because they are randomly assigned. Letter B. In an accountability study, a group of students in an English composition course is given a pretest. After the course, the same students are given a post-test covering similar material. Are the two groups of scores independent or dependent? All right, so in this case, they are dependent samples. And this is because we have the same students doing both tests. All right, so you have a theorem here. It says that x1 and x2 have normal distributions with means mu1 and mu2 and standard deviations sigma 1 and sigma 2 respectively. If we take independent random samples of size n1 from the x1 distribution and of size n2 from the x2 distribution, then the variable x1 bar minus x2 bar has a normal distribution, mean mu1 minus mu2, standard deviation sigma 1 squared divided by n1 plus sigma 2 squared divided by n2 squared, the square root of that sum. If both n1 and n2 are 30 or larger, then the central limit theorem assures that x1 bar and x2 bar are approximately normally distributed. We have a formula for the margin of error, and this is our z critical value times the square root of our sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. When we're doing a confidence interval for mu1 minus mu2, when both sigma 1 and sigma 2 are known, we let sigma 1 and sigma 2 be the population standard deviations of populations 1 and 2, obtain two independent random samples from populations 1 and 2, where x1 bar and x2 bar are sample means from populations 1 and 2, m1 and n2 are sample sizes from populations 1 and 2. If you can assume that both population distributions, 1 and 2, are normal, any sample sizes n1 and n2 will work. If you cannot assume this, then use sample sizes n1 greater than or equal to 30 and n2 greater than or equal to 30. And so here's our confidence interval formula. Our point estimate is x1 bar minus x2 bar plus or minus that margin of error, z critical value, times the square root of sigma 1 squared divided by n1 plus sigma 2 squared divided by n2. All right, so here's our next practice. In the summer of 1988, Yellowstone National Park had some major fires that destroyed large tracts of old timber near many famous trout streams. Fishermen were concerned about the long-term effects of the fires on these streams. However, biologists claimed that the new meadows that would spring up under dead trees would produce a lot more insects, which would in turn mean better fishing in the years ahead. Guide services registered with the park provided data about the daily catch for fishermen over many years. Ranger checks on the streams also provided data about the daily number of fish caught by fishermen. Yellowstone today indicates that the biologist's claim is basically correct and that Yellowstone anglers are delighted by their average increased catch. Suppose you are a biologist studying fishing data from Yellowstone streams before and after the fire. Fishing reports include the number of trout caught per day per fisherman. A random sample of N1 equals 167 reports from the period before the fire showed the average catch was X1 bar equals 5.2 trout per day. Assume that the standard deviation of daily catch per fisherman during this period was sigma 1 equals 1.9. Another random sample of N2 equals 125 fishing reports 5 years after the fire showed the average catch per day was X2 bar equals 6.8 trout. Assume that the standard deviation during this period was sigma 2 equals 2.3. So I'm just going to highlight these different samples in different colors. So we have our N1 is 167, our X1 bar is 5.2, and our sigma 1 is 1.9. Then we also have that our N2 is 125, our X2 bar is 6.8, and our sigma 2 is 2.3. And we have for both of these that they were random samples, which is important. All right, for each sample, what is the population? Are the samples dependent or independent? Explain. Is it appropriate to use the normal distribution for the X1 bar minus X2 bar distribution? Explain. So we have our N1 is before the fire, and N2 is from after. They are independent. Because independent random samples are from before and after. We have that both N1 and N2 are greater than 30, so it's okay to use the normal distribution. All right, we do 95% confidence interval for mu1 minus mu2, the difference of the population means. So first we need this 95% confidence. We need that Z critical value. So our Z of 0.95, this is going to give us 1.96. So if I plug this into our formula, we have X1 bar minus X2 bar plus or minus our Z critical value times the square root of sigma 1 squared divided by N1 plus sigma 2 squared divided by N2. All right, so we have 5.2 minus 6.8 plus or minus 1.96 times the square root of 1.9 squared divided by 167 plus 2.3 squared divided by 125. All right, 5.2 minus 6.8, this is negative 1.6 plus or minus. When we multiply all this together, we get 0.50. So we end up with negative 2.10, comma, negative 1.10 for our confidence interval. Notice that these are both negatives. And we'll talk about what that means in the interpretation part. I also want to go over how to do this in the calculator. So if you're doing this in the calculator, we're going to go to the menu where we go Stat, Tests, and we're going to go down to number 9, which is the 2 sample Z interval. So again, it's number 9. It's the 2 sample Z interval. Now when we enter our data here, first you're going to put in sigma 1, which is 1.9, sigma 2, which is 2.3, X1 bar, which is 5.2, N1, which is 167. Then we have X2 bar, which is 6.8, N2, which is 125. Our confidence level is 95 here. And when we do this in the calculator, we end up with negative 2.096, comma, negative 1.104. 4. So almost exactly what we got using our formula. All right, so what is the meaning of the confidence interval computed in part B? So we would say we are 95% sure that mu1 minus mu2 is less than 0, which means mu1 is less than mu2. So more trout after the fire, because that was represented by mu2. Okay, we did 2 types of intervals, if you recall, for our means. So the same will apply when we're comparing 2 means. So now we're going to look at the t variable. If you notice the t variable, we have a formula that looks similar, just now we have the 2 variables. Our margin of error is almost identical. The only difference now we have TC instead of ZC. And then we have our S for our standard deviation, because again, we're representing the sample, not the population. And so let's go to the next page, and here's our confidence interval formula. Again, we obtained 2 independent random samples from populations 1 and 2, where our x1 bar and x2 bar are sample means from populations 1 and 2. S1 and S2 are sample standard deviations from populations 1 and 2. M1 and N2 are sample sizes from populations 1 and 2. If you can assume both are normal, any sample size will work. If you cannot, then use sample sizes N1 is greater than or equal to 30 and N2 is greater than or equal to 30. So here's our full confidence interval formula. Same as what we just did, except now we have our t critical value and our S1 and S2 sample standard deviations. Notice TC is the critical value for confidence level C with degrees of freedom using the smaller of N1 minus 1 and N2 minus 1 or the calculator approximation. We're going to do the calculator approximation here. All right, Alexander Borbely is a professor at the Medical School of the University of Zurich, where he is director of the sleep laboratory. Dr. Borbely and his colleagues are experts on sleep, dreams, and sleep disorders. In his book Secrets of Sleep, Dr. Borbely discusses brain waves, which are measured in hertz, the number of oscillations per second. Rapid brain waves, or wakefulness, are in the range of 16 to 25 hertz. Slow brain waves, or sleep, are in the range of 4 to 8 hertz. During normal sleep, a person goes through several cycles. Each cycle is about 90 minutes of brain waves, from rapid to slow and back to rapid. During deep sleep, brainwaves are at their slowest. In his book, Professor Borbely comments that alcohol is a poor sleep aid. In one study, a number of subjects were given a half liter of red wine before they went to sleep. The subjects fell asleep quickly, but did not remain asleep the entire night. Toward morning, between 4 and 6 a.m., they tended to wake up and have trouble going back to sleep. Suppose that a random sample of 29 college students was randomly divided into 2 groups. The first group of N1 equals 15 people was given a half liter of red wine before going to sleep. The second group of N2 equals 14 people was given no alcohol before going to sleep. Everyone in both groups went to sleep at 11 p.m. The average brainwave activity, 4 to 6 a.m., was determined for each individual in the groups. Assume the average brainwave distribution in each group is mound-shaped and symmetric. The results follow. So here we have group 1. We see our N1 is 15. This was the group with alcohol. And we have our average brainwave activity listed here. We also have our group 2. Notice this one has N2 is 14. This is the group without alcohol. So I want you to enter group 1 into your L1 in your calculator and group 2 into your L2 in your calculator. When we check the requirements, it says, are the samples independent or dependent? And explain, is it appropriate to use a t distribution to approximate the x1 minus x2 distribution? Explain. So these are independent. Again, we have random assignment. And there's no association. between the group members. And yes, we can use the t-distribution. Because both are mound shape and symmetric. All right, letter B here. Compute the sample mean and sample standard deviation for group 1 and group 2. Go ahead and do that. All right, we should get that our X1 bar is 19.65 and our S1 is 1.86. Our X2 bar is 6.59 and our S2 is 1.91. So now we need a 90% confidence interval for mu1 minus mu2, the difference of population means. So for this one, I'm going to show you how to do this one in your calculator because we already entered all the data there. So you're going to go Stat, Tests, and this time you're going to go down to choice 0, the 2 sample t interval. So I'm going to do 2 sample t interval, and it's choice 0 on your calculator. And we're going to do this with data this time because we already entered our data into our calculator. So by list 1, it should say L1. By list 2, it should say L2. Leave the frequencies both as 1, and then your CL for confidence level, we're doing this one as 90%. When your calculator asks about pooled, you want to make sure you choose no. We are never going to do it pooled. All right, go ahead and hit calculate, and it should come out to give you 11.868, 14.254. Again, noting this time that both are positive. All right, if we turn the page to interpret this, what's the meaning of the confidence interval we just computed? We would say we are 90% confident that mu1 minus mu2 is greater than 0, or mu1 is greater than mu2, which means more brainwaves from 4 to 6 a.m. with the alcohol. All right, so how to know which distribution to use. So here we have that you examine the problem statement. If your mu1, or excuse me, your sigma 1 and sigma 2 are known, then we're going to be using our 2 sample Z interval. If our sigma 1 and sigma 2 are unknown, that means we use S1 and S2, the sample standard deviations instead. And so that means we're going to use the 2 sample T interval. Again, for each of these, you can use the formula or you can use the calculator. The last scenario over here is when sigma 1 and sigma 2 are unknown, but there's reason to believe they are the same. This case is very rare. And it says use the t-distribution with pooled estimate. If you were to do a specific problem, they would tell you that your sigma 1 and sigma 2 are the same, and that's the only time you'd use the pooled where it would be yes. okay? So again, only in rare cases, and you would be told if that was going to be true. All right, now we're going to look at another theorem. Now we're looking for proportions. So consider two binomial probability distributions. We have our N, R, P, Q, P hat, Q hat, all defined here for both distributions 1 and 2. Again, number of trials should be sufficiently large so that the N times P hats and are each greater than 5. So it says that our R1 divided by N1 minus R2 divided by N2 has approximately normal distribution. The mean is P1 minus P2. So again, I'm going to point these out for you. And standard deviation is approximately, we have square root of, it looks like the formula we did before, we're just adding again. So P1 hat times 1 minus P1 hat over N1 plus P2 hat times 1 minus P2 hat divided by N2 and the square root of all of that. So our confidence interval, here we have basically that point estimate, P1 hat minus P2 hat, plus or minus our z critical value times that standard deviation we just described, okay? Again, remember this n times p, this just means our number of successes and the number of failures are both greater than 5, okay? In his book, Secrets of Sleep, Professor Borbely describes research on dreams in the sleep laboratory at the University of Zurich Medical School. During normal sleep, there's a phase known as REM, or rapid eye movement. For most people, REM sleep occurs about every 90 minutes or so, and it's thought that dreams occur just before or during the REM phase. Using electronic equipment in the sleep laboratory, it is possible to detect the REM phase in a sleeping person. If a person is wakened immediately after REM phase, he or she usually can describe a dream that has just taken place. Based on a study of over 650 people in the Zurich Sleep Laboratory, it was found that about 1/3 of all dream reports contain feelings of fear, anxiety, or aggression. There is a conjecture that if a person is in a good mood when going to sleep, the proportion of bad dreams, fear, anxiety, aggression, might be reduced. Suppose that two groups of subjects were randomly chosen for a sleep study. In group 1, before going to sleep, the subjects spent 1 hour watching a comedy movie. In this group, there were a total of N1 equals 175 dreams recorded, of which R1 equals 49 were dreams with feelings of anxiety, fear, or aggression. In group 2, the subjects did not watch a movie but simply went to sleep. In this group, there were a total of N2 equals 180 dreams recorded, of which R2 equals 63 were dreams with feelings of anxiety, fear, or aggression. So I'm just going to highlight our different groups. So our group 1, N1 is 175, and our R1 is 49. Our group 2, we have R2 is 63 here, and our N2 is 180. So from these, we can find our P hats. So P1 hat is R1 over N1. This is 49 divided by 175, which is going to give us 0.28. And then our P2 hat, this is our R2 divided by N2. And so for this one, we have 63 divided by 180. And this is going to give us 0.35. All right, checking our requirements. Why could groups 1 and 2 be considered independent binomial distributions? Why do we have a large sample situation? So we have randomly chosen different groups. So that means it's independent. And our number of successes, which remember is just our R value. So our R1 is 49, our R2 is 63. Those are both greater than 5. Our number of failures, so we have 175 minus 49, which is 126. And 180 minus 63, which is 117, both of those are also greater than 5. What is P1 minus P2? Compute a 95% confidence interval for P1 minus P2. All right, so again, we want 95%, so our Z of 0.95 is going to give us 1.96. And if we are doing our confidence interval, we'll write this one out. So we have P1 hat minus P2 hat plus or minus our Z critical value times the square root of P1 hat times 1 minus P1 hat all over N1 plus P2 hat times 1 minus P2 hat all over N2. All right, we have 0.28 minus 0.35 plus or minus 1.96 times the square root of 0.28 times 0.72 divided by 175 plus 0.35 times 0.65 divided by 180. All right, our point estimate comes out to be negative 0.07 plus or minus, for this margin of error, we get 0.0963. First we subtract and then we add, so we have negative 0.1663, comma, 0.0263. And what's important to note on this one is that this interval goes from negative to positive. All right, if you're doing this one in the calculator, you're going to go stat over to tests, and this time you're going to choose choice B. It's the 2 proportion Z interval. And again, it's choice B. So you'll enter your X1, which remember is like R1. So that's 49. Your N1, which is 175. Your X2, which is like R2. So that's 63. N2, which is 180. And then our confidence level, we want 95% for this one. So we'll enter 95. And so then when you do this in the calculator, you end up with negative 0.1663 up through 0.02634. So only difference is it goes one more decimal place on the upper bound. You'll also note it does tell you your P1 hat on the screen, which is 0.28, which verifies we calculated correctly, and it tells you your P2 hat, which is 0.35 on that screen. You don't need to write those down. I'm just pointing out that they are accurate with what we calculated. All right, so now we need to interpret this. What is the meaning of the confidence interval constructed in part B? So we would say because our interval from negative 0.1663 to 0.0263 contains 0, we cannot conclude a difference in the proportions who experienced bad dreams. Okay, so in general, when we are looking at these and comparing them, this applies for the P's and for our mu's. If our P1 minus P2 is less than 0 or negative, that means that P1 is less than P2. Okay, so again, that's when Both are negative. If your P1 minus P2 is greater than 0, that means P1 is greater than P2. And again, this is when both are positive. And I'm talking about the endpoints of the interval here. The last case we'll have, P1 is equal to P2. Oops, I'm sorry, I wrote that a little too early. I should say P1 minus P2, if it can equal 0, if there's one negative and one positive, that means our P1 could equal P2. And again, this is when you have one negative, so your lower bound is negative, and one positive being your upper bound. All right, so let's try to interpret these. A says a study reported 90% confidence interval for the difference of means to be 10 to 20. For this interval, what can you conclude about the respective values of mu1 and mu2? So if you notice here, 10 to 20, both values are positive. So what that means is our mu1 minus mu2 is positive or greater than 0 because both our lower and upper bound were positive. So we are 90% confident that our mu1 is greater than mu2. B says a study reported 95% confidence interval for the difference of proportions to be negative 0.32 through positive 0.16. For this interval, what can you conclude about the respective values of P1 and P2? I want you to conclude this one. All right, here we could say because 0 is in the interval, we cannot conclude if one proportion is larger than the other. And again, this is because they could be equal to each other. And that is the end of our notes for today.